Welcome to this course on discrete structures in computer science. It's a quite fascinating subject which spans across almost every field in computer science. This is one of the fundamental courses which acts as a strong foundation, and all other courses they build on top of this. The courses such as discrete mathematics, data structures and algorithms, automata theory, and you have computer organization. If you see these four, they act as the foundation for this multi-story building, namely computer science. The other courses, they build on top of this. For example, you have a course on operating system, you have a course on computer networks, you have a course on database management systems, then something called compiler design. And this lattice one can keep growing. And on top of this, you find system related courses such as computer architecture, high performance computing, and applied courses such as machine learning, artificial intelligence, image processing, and so on. So, in a nutshell, and as you are all entering into the field of computer science, one should be familiar with these four thoroughly. And once you get this foundation right, building other structure on top of it, doing other courses, system courses, applied courses, application level courses, and all that would be quite comfortable. And what is so special about this course, discrete structures? We use discrete structures, discrete mathematics, discrete structures in computing, discrete structures in computer science, discrete structures in computer science and engineering. All these phrases are used interchangeably. They all mean one. They all talk about a collection of concepts, and which are quite powerful and very heavily used in the field of computer science. Okay. And being a mathematics course, we ask questions out of curiosity. We ask questions out of curiosity. We ask good questions. We ask fundamental questions. For example, one can ask, is there a science in computer science? So, when was computer science born? How was computer science born? And in an attempt to answer this question, we get insights. We get insights into the concepts, into the subject, and the insights that we gain out of these questions, in an attempt to explore, we get insights, and that will tell you more about this subject, how exactly it is a foundation course and why it is a foundation course, and how other subjects are all sitting on top of this. We may not answer all of them in this course itself, but at least an attempt will be there, a partial answer we will get as part of this course. May not be immediately, and at various stages of this course, we get to see the answer to this question. But at the end of your 4-year program, you will indeed appreciate these questions and the answers to all of this. Okay. One can also ask other questions. Having said discrete structures, discrete mathematics, one can ask, is there something called continuous mathematics? Okay, so questions like this we are interested in, and this will keep us busy maybe one full semester. Okay. At the top level, the term discrete in discrete mathematics, it focuses on discrete sets, namely the set of natural numbers, the set of the rational numbers. The term continuous in continuous mathematics refers to continuous sets such as the set of real numbers and the set of complex numbers. Okay, and we also come across very interesting sets as part of this course, not just the natural numbers, real numbers, and so on. We would like to know things like this: set of all C programs, set of all inputs to an algorithm. We wish to know, is this discrete or is this continuous? And so this tells you, when you write a C program, we may find more than one way of writing it. So we may find many ways of writing it. Now you take all possible C programs that you can see, and we ask what is the size of the set, and we want to count how many inputs one can give to a fixed algorithm. So questions like this we want to address, and things like this you can see it from math perspective. Questions like this one can see from the applied perspective, the applied in the field of computer science and engineering. So, having given introduction to computer science and the course discrete structures, let's get into the details. So, as part of this course, we will be learning a formal language, the language that we speak, the English, we call it as a natural language, English, German, and so on. But we need a different language for various reasons, to bring in formalism, the way we speak, the way we represent things, to interact with computing machines such as calculators, laptops, desktops, workstations, high performance computing machines, and so on. So we need a formal language, not just for communication between humans, we also need to communicate with machines. And so you have human-human interaction, you have human-computer interaction, and you also have machine-to-machine interaction. So computers are interacting to each other, for example, computer networks, and two machines in a cloud network is interacting without any human intervention. So for all that, we need a formal language. So we study something called logic. Just like English, German, we study a language called logic, which will tell you how to speak, how to write in a formal way. Then we will get into discrete structures. we will talk about sets, we talk about relations among elements, which we call it as relations, and then we talk about a special relation called functions. One can represent these relations, functions, in a graphical way, which is a quite powerful model, which itself is an interesting field in the field of computer science, namely graph theory. So along the line, we will also look at counting. We also look at a bit of linear algebra. So to set the context, we will talk about logic for a while. Then we will talk about how to represent sets formally using the logic that we have learned. Then subsequently, using the sets, we talk about something called relations. Then we talk about special relations. Then when we discuss relations and functions, we need a representation, a graphical representation, wherein we bring in the field graph theory. And while we discuss all of this, we will come across sets which we want to count. So we will also look at counting. We will also make claims, we will make observations, we will bring out properties and so on. So we will look at proof techniques. So this will be the focus of this course. So what we will do, we will start with logic, and then we will get into the details of other modules. Okay. There are at least there is something called there are at least three different types of logic. There is something called zeroth order logic. This is also known as propositional logic, and there something called first order logic. This is also known as predicate logic. Then there is something called second order logic. We also have something called monadic logic, and so on. So as part of this course, we will discuss the first two items, and things like second order logic, monadic logic, we will see in subsequent courses. So we will be talking about these two, and in particular, what is a proposition and what is a predicate, and our propositions and predicate helping us in expressing statements, expressions, and so on. So just like the way a natural language evolved, for example, if you look at any natural language for that matter, this is how the evolution was. We discover alphabets, then we combine them to make words, then we combine this to get sentences, then we make paragraphs, and you make chapters, textbooks, and so on. So this is how it grows. This is in the context of natural language. We want to follow a similar scheme and see how exactly this language logic was evolved. So which means we will have to introduce some basic terminologies, some notations. Then with that, how do we frame words, sentences, and so on. So let's explore logic from now on. So having given the introduction to computer science and the logic, we will see some basic definitions and which we will use heavily, and then we will get into the details of first order logic. So the terminologies that we use in zeroth order logic and first order logic. Okay, there is something called assertion. What is an assertion? An assertion is a statement. For example, I say 2 plus 4 equals 6, and I say today is Monday. Okay. I say E equals mc square, and every prime number is not divisible by 4. So we make statements, we make generic statements, mathematical statements like this, and so on. So it is just a statement. We have something called proposition. So proposition is an assertion, or proposition is a statement that takes some truth value. See, in natural language like English, when we utter statements like this, we don't associate a truth value. For example, is it true, false, and so on. Whereas in first order logic, we are interested in the meaning. We are interested in the semantics. We are interested in the truth value. So the truth value associated with a statement, it can be true or it can be false. So what is a proposition? So proposition is an assertion or a statement that takes the truth value either true or false, but not both. It takes the truth value either true or false, but not both. Okay. And when we talk about statements, we talk about, most importantly, declarative statements. Something like this. The other statements, so not discussed as part of this. So we don't talk about statements, say, such as imperative statement. You make an order, bring a pen drive, get me a cup of coffee. And we also do not take statements and is it a 3-credit course, something that involves a question we don't discuss, and something that expresses the emotion, for example, aha, today is a festival day. So we don't talk about uh, statements of this type as part of first order logic. So our focus is only on declarative statements, and to that declarative statement you associate a truth value, either true or false, and we call it as a proposition. So the statement over here refers only to declarative statement. Okay. So as part of first order logic, our focus is on declarative statements, and given a declarative statement or an assertion, and we want to know, does it take the truth value true or false but not both, then it becomes a proposition. There are statements for which you may not be able to decide its truth value, and they are just declarative statements. You may not call them as propositions. We will see a couple of examples on this front. So look at this. 2 plus 4 equals 6. It's a declarative statement. It is not falling into any of them, and it is always true. So this is true always, which means it is a proposition. When we say either true, it is always true. It is true always and not dependent on the context. So always true, independent of the context. We'll see an example now. For example, today is Monday is a declarative statement. However, if you see this statement on a Monday, then it is true. If you see on some other day, it is false. So which means it can take true or false, depends on the context. So which means this is not a proposition. So E is equal to mc square is true always. So this is a proposition. And every prime number is not divisible by 4. This is also true always. So this. So when we make statements, we want to make declarative statements. Then we want to associate a truth value such as these two, either true or false. If a declarative statement is depend on the context, some context, for example today is Monday, then we don't take such things as part of this. So let us see some more examples, and then we build things on top of proposition, which we will see